there's any questions from, it's like 51 to 84-ish. I say ish because there's lots of them that you got to skip in there. But if there's any questions there, Valerie? 57. So this question asks to determine whether that point lies on the line. Thank you.
Do you buy that?
Oh, I don't think so.
How about that?
Maybe.
Don't buy this. Buy that.
Yeah.
Okay.
Okay. Thank you. Okay. So, if we look at the linear combination form, so Val, the I vector represents which component? The I vector represents the x component. Yep, that's all we're saying. So if this is true, then negative 10 should equal 1 minus 4t. And the j vector represents the y component. So 17 should equal 3 plus 7t. And if I solve this for t and get the same value for t, then yes, this point would be a point on my line. If the values for t disagree or differ, then no, it wouldn't be a point. So let's see, what do I get? I get 11/4 equals t, and then I get 2 is equal to t. So no. That's not a point on the line. Is that cool? Yeah. So just in terms of if it's easier to write this in the other form, you're welcome to do that too. So here is my point vector, and then here is my slope vector. So you can think about it just putting it back into the other more familiar form. If that's easier, you can think about it that way as well. Okay. You're welcome. Again, just the i's are the x's and the j's are the y's. Okay. Lindsay. Which one? 80? Sure. Oops. All right, so 80 asked for 5, -3, -6. So I'm going to start by plotting 5 tick marks on the positive end of the x-axis. I'll put 3 tick marks on the negative end of the y-axis, and 6 tick marks on the negative end of the z-axis. Good with that. All right. So I'm going to start by just drawing a line starting from that last tick mark on the x-axis that's parallel to the y-axis. And I'm going to do the same thing starting at the last tick mark on my y-axis. I'm going to draw a line parallel to my x-axis. So this then becomes like the top of my box. Cool with that. And if I was just operating in 2 dimensions, that would be the point that I'd be interested in right there. Okay? So what I'm going to do now is I'm going to project this down 6 units. So this one is going to come down 6 units. This one is going to come down 6 units. That's going to come down, got a little messy on me. come down 6 units, of course. And that one's going to come down 6 units. So there's the bottom of my box. Okay with that, Linz? So the point that I'm interested then in is this one. Is that okay? So this was the one we were interested in, 2 dimensions, and I've just projected it down 6 units. So if it's like the upper left-hand corner of the top of the box, it's going to be the like upper left-hand corner for the bottom of the box. Does that make sense? Okay. So it's like the same in the same spot, so to speak. Does that feel okay? Okay. Meg?
If we follow the line and just did the.
I want to see the whole box.
Oh.
Okay. It's much easier for me to check if I see the whole box. Lindsay?
So for the first part, it's positive down
Okay, so you got to think about it in 3 dimensions, right? So that dashed line is the part that we've drawn on is the part that's coming out of the board towards you, and the dashed part that we didn't draw on is going behind the board into Miss Garcia's classroom. And so there's not really 4 quadrants anymore. There's 8 quadrants. So you have 4 quadrants in the positive half of the Z and then 4 quadrants in the bottom half of the Z. So I know what you're asking me, and I really would encourage you not to think about it that way. And you have to look at it kind of like one of those magic eye pictures where you have to stare at it for a minute before the three dimension kind of clicks in and you can see it in space. And that usually helps make things a little bit easier if you can get away from trying to think about it as flat. I know that wasn't exactly the question you're trying to answer, but I feel like I was getting at the root of it. Okay. And I'm sorry to cut you off, but I heard where you're going, and it's I don't like where this is heading, so I wanted to stop you there. Is that okay? Who's next? Megan? 73?
May I go to that one now, please?
Of course.
That's okay.
Okay, so this was the problem, right? I copied that down, right? All right. So if I look at equation 1, my x component is 2 plus 2t. And in equation 2, my x component is 3 plus 3t. You agree with that, Meg? Okay. And then we'll look at the y component. So in equation 1, that's negative 2 plus 4t. And then in equation 2, that's 1 plus negative 5t. Oh my goodness. This first equation is supposed to be in S, isn't it?
Look at this.
Great googly moogly, Mr. Kulik. So I'll try to draw those more like an S and less like a 5, but I know my 5s and S's look pretty similar. All right. So what I'm going to do now is I'm going to get all my variables on one side and all the constants on the other. So here I'm going to have 2s minus 3t is equal to 1. And over here I'll have 4s plus 5t is equal to 3. Agree with that, Meg? Okay. I'm going to turn this into a matrix, or this system of equations, I guess, into a matrix. And I'm going to solve this using the row reduced echelon form command on my graphing calculator. I don't know why I put a 1 there. That's definitely supposed to be a 2. Anytime you want to open, you stupid calculator app. All right, so to enter this in, I'm going to go into the matrix menu, go over to the Edit tab, pick one of the matrices, it doesn't matter which one. Our matrix has 2 rows, 1, 2, and then 3 columns. So if it wasn't formatted 2 by 3, I would change its format to reflect that. And then I'm just going to type in the rows exactly as they appear on my paper. And then I'm going to exit back out to the main menu. To retrieve the RREF command, that's located inside of the matrix menu. So I'll go back in there. But this time I'm going to go over to the Math tab. And then it's one of the last commands, so I usually go down to get, or wrap around to go get it. So there it is. And then I'll just do that on matrix A. And that's not an appealing looking answer to me with all those crazy decimals. But if I do the math frac command, stop talking please, it'll give this to me as a fraction, which is a whole lot nicer. So what this tells me is S is 7 over 11, and then T is 1 over 11. But that's not my point, right? Those are parameters to my equations, which will allow me to find my point. So if I go back to, say, equation 1, armed with the fact that S is equal to 7 over 11, and I plug that in, I get 2 plus 2 times 7 over 11, and then negative 2 plus 4 times 7 over 11. And I get some gross fraction, which would be the points here. What are those going to be? 36 elevenths and 6 elevenths. No, the T is 1 over 11. That's okay. That's a good question. Again, easy to make that mistake. S is the same parameter. S is just one number. If I were to use the other equation, then I would use 1 over 11 for T in both the X and Y component. Okay with that? Megan, does that do it for you?
Yeah.
Okay. Lindsay.
Does it matter if it's all good?
No, you should get the same answer either way, which is a decent check, right?
Yeah.
So if you're not sure you did it right, try the other parameter and make sure you get the same point both times. Now these ones that have fractions in it, you're just as likely to make a fraction error as you are to have made like some other procedural error along the way. So I don't know how great of a check it is in those cases, but your calculator should be able to handle it. You know what I mean? Anyone else? Questions from this? Homework. These were good ones, though, guys. You asked about good problems. You asked good kinds of questions. Like the how do I think about this questions are the good ones. Right? Because that's what we want to be able to do, is we want these problems to seem easier by thinking about it like in a clever ways.
You watch this before?
A little. I was still awake when the halftime show was going on.
Did you enjoy the halftime show?
I don't know.
Shakira or J-Lo?
It felt very inappropriate for television.
I enjoyed it.
Good to know.
I'm not a complainer.
I'm more of a Shakira guy myself.
I am as well.
Jamie's more of a J-Lo guy.
Okay.
I love the J-Lo side.
Thanks for the updates, guys. Sounds like we're done with questions from the... Yes, Micah.
So do you do 2 plus 2 and then times it by 7 over 11 to get 36 over 11?
No, you do the order of operations.
So you just do it to roll? Or do you only do it to 1, 2?
Yeah, you do 2 times 7 over 11,
Okay.
and then you add the other 2.
Oh, so you only multiply to 1.
Yes, because that's what I wrote down, right? If I was doing what you were doing, I would have to do that. You know what I mean? Okay. All right. All right, moving on. On to section 6, where we're going to talk about 3D vectors. I need you guys to stop talking, though, please. So there's 3 different forms that we use to represent vectors. So there's component form. In 2 dimensions, component form was the wedge brackets and then like an A and a B. If for 3 dimension, it's going to be the same thing, except we have a 3rd component. So we just have A, B, and C. The IB component form, or the column vector, column A, B, C. And then our linear combination form. Remember, the vector I represented the X component. The vector J represents the Y component. And we're going to use the vector K to represent the Z component. We're just following in alphabetical order. So I, J, and K are unit vectors. Remember, I is the vector 1, 0, 0. J is the vector 0, 1, 0. And K is the vector 0, 0, 1. So, for example, let's say that we have the points 3, 8, negative 4, and then B is the point negative 5, negative 6, positive 1. And we want to write the vector AB. So how did we do a problem like this in 2 dimensions? Yeah, we used the head minus tail method, right? So which of these 2 points, A or B, is the terminal point for my vector? B, right? How did I know it was B? Yeah, it's the one that the arrowhead is over. So I'm going to do negative 5 minus 3, and then negative 6 minus 8, and then positive 1 minus a negative 4. Everybody good with that? So just like we did in 2 dimensions, right? What if I wanted to write this in IB component form instead? How would I write it? Well, I just write it as a column vector, right? Stop talking, please, fellas. Or what if I want to write this in linear combination form? Well, I just... Yes, of course. So I'm just going to replace the x, or I'm going to pair with the x component and vector I, with the y component vector j, and with the z component vector k. Yes. Nope, because you were talking the whole time. I'm sure if you looked before or after, you could figure out what that one number must have been. Okay. What if I then wanted, say, the magnitude of vector AB? In 2 dimensions, how do we find the magnitude? Good. The square root of the first component squared plus the square root of the, plus the second component squared. So if we have 3 components, how's this going to change? Not much, right? You just, instead of having the sum of 3 squares, or instead of the sum of 2 squares, you have the sum of 3 squares. I think that comes out to 269. I'm just asking you to do a bunch of things. Okay, so in 2 dimensions, when we talked about direction, we're looking for like a unit circle angle, right? Yeah. Now, if we project a circle into 3 dimensions, it's a sphere. How many angles do I need to describe a direction inside of a sphere? You need 2, like latitude and longitude. And you know what we're going to do? We're not going to do this in this class. As it's a non-trivial conversion to go from, to go between those 2 different representations. That is a completely different question.
We're not learning.
We're not finding
No, I would. Not.
All right. So let's say that u is the vector -2, 4, 7, and v is the vector 7, -6, -9. And we're interested in the vector 2u plus v. So when we did scalar multiplication in 2 dimensions, how did we do that? You multiply the scalar to each component, right? Do you think that changes in 3 dimensions? No. And then I'll just convert that linear combination form into component form. Now, when we added vectors in 2 dimensions, how did we do that? Yeah, you added each component, right? You add the x's, add the y's. Suppose you add a 3rd component here. What do you think you're going to do? Yeah, just add the component still. Everybody's good there? Okay? And let's say I'll just call this W, this vector W for the sake of argument. What if we wanted to graph that vector W? In 2 dimensions, how did we graph a vector in component form?
I forget. Something with cosine.
There was no cosines needed. Right, you just plotted the point and drew a line from the origin to that point, right? Guess what we're going to do in 3 dimensions? Same thing. All right. So how do we plot the point 3, 2, 5? This is not down, though. This is the positive direction on the x-axis. Okay.
Then 2 on the x-axis.
That's the y-axis.
Y-axis.
Again, remember, guys, x, y, z.
I'm never gonna.
That's so dumb. You never made that.
Okay, so first thing I do is I'm going to draw a line that's parallel to the y-axis, starting at that last tick mark I made on the x. And then starting at the last tick mark I made on the y-axis, I'm going to draw a line parallel to the x-axis. Okay. Everybody good there? This gives me the bottom of my box here. Everybody good there? Bless you. So I'll go up 5. Oops. Oh dear. Go up 5, up 5, then up 5. So there's my box. Now in 2 dimensions, this was the point that we were concerned with down here, right? If I project it up to 3 dimensions, there's the point that I'm interested in, right there. Everybody good there? So my vector then, let's use that one. Is that. Everybody okay there? So just like before, I go from the origin to the point, right? So next up, we're going to talk about 3D vector equations for a line. We did this in 2 dimensions. So in 2 dimensions, we said r is equal to r naught plus v, where r naught is our point vector, and v is our slope vector. But if we extend this to 3 dimensions, what does slope mean in 3 dimensions? Yeah, rise over run doesn't make any sense anymore in 3 dimensions, right? Yeah, so slope doesn't really have a 3-dimensional counterpart, But what we can do is instead of giving us the slope or using a slope vector here, what is the slope vector really telling us? So imagine we're in 2 dimensions. We have some point. What the slope does is it tells us how to get to the next point, right? Everybody agree with that? What is this the same as giving? It's the same thing as giving the direction for the vector. Everybody agree with that?
Stop.
That is something that has a 3-dimensional analog to it and makes equally as much sense in 2 dimensions as it does in n dimensions. Although in this class we won't go beyond 3, but you could certainly have an n-dimensional vector, which is pretty rad. So let's do an example and show you how this actually works in practice. Let's say we want the equation through the points (5, -2, +6), and then -3, +4, +1. So to write this equation for a line, I need to write r is equal to r0 plus vt. R is a point vector. There's 2 obvious choices for vector r0. What are those 2 obvious choices? Well, there's vector A or there's vector B. Does it matter which one you use? Definitely doesn't. So pick whichever one you feel better about. Everybody feel good there? That's easy, right? So our direction vector, there's 2 obvious choices for this. Those 2 obvious choices would be the vector AB or the vector BA. Does it matter which one you choose? No? So let's just make some decisions right quick here. Let's use this one and this one, just for the sake of this example. Sound good to you guys? Okay. So AB is going to be head minus tail. That's going to give me -8, +6, -5. So point vector plus direction vector times t, and we're done. What do you guys think? That was pretty easy, right? There wasn't much to do there. Might have even been equally as easy as the 2-dimensional situation, right? Yeah, not much difference. What if we wanted to figure out if a point in 3 dimensions lies on this line? Do you remember how we did this in 2 dimensions?
Yeah.
Yeah, we set the x's and y's equal to the values for the point, and then solve for t and see if we got the same t, right? So we'll, no, it is not the ref. It was not that. Marche, that was for finding the intersection. Yep. Got them all cut. Everybody okay with what I did there? Now all I'm going to do is solve for t and see if I get the same value back. So in each case, I get -2 for t. What does that tell me? Yes, that's a point on our line. Lynn, what's up? Oh, okay. I couldn't tell if that was a hand or what was going on there. You're good. Do whatever you want. All right. Any questions on this? Let's stop here. We have